Up next, we're going to take a look at infinite limits. And the first type of infinite limit we're going to look at are horizontal asymptotes, which really are just the end behavior of a function. By end behavior, if you look up at the graphic, I'm talking about what's happening to my y values as x gets really, really big and positive, or as x goes to negative infinity, really, really big and negative. If you remember, we talked about thinking about infinite limits as a race between the numerator and the denominator. For example, if your numerator is bigger than your denominator, your y values are getting really, really big. And if your denominator is bigger than your numerator, you're looking at a fraction like 1 over a million, which is really close to 0. And the way we figure out which is bigger is by looking at the degrees of our numerator and denominator. Here we see that our numerator has a degree of 1 and our denominator has a degree of 2. That means our denominator is much bigger than our numerator and gets increasingly bigger as x goes to infinity. When we have a smaller number divided by a really big number, our limit goes to 0. If my y values are approaching 0 as x goes to infinity, that means I have a horizontal asymptote at y equals 0. Here we look at our numerator and denominator and see that they both have a degree of 2, meaning they're both growing at a similar rate. When this happens, we look at the ratio of our leading coefficients. Here, the ratio of our leading coefficients is 4 over 1. And so our limit is approaching 4. The numerator is usually 4 times as big as the denominator, and it gets closer and closer to being exactly 4 times as big as x goes to infinity. This also means that we have a horizontal asymptote at y equals 4. And then our last example is when we have a degree of 2 in our numerator and a degree of 1 in our denominator. Here we're top heavy, meaning that our numerator is getting bigger, much faster than our denominator, turning this into a really, really big number that approaches infinity. That means because our limit approaches infinity, that we have no horizontal asymptote. Our y values never level out, they just keep getting bigger and bigger. I want to take a minute to write down the formal definition of a horizontal asymptote, which is really what we've been working with. It says if the limit as x goes to infinity of f of x equals b, or if the limit as x goes to negative infinity of f of x equals b, then the horizontal line y equals b is a horizontal function of our function, as a horizontal asymptote of our function f of x. What this is saying is that as x gets really, really big, if we level out to some y value b, or as x gets really, really negative, if we level out to some y value of b, then that line y equals b is a horizontal asymptote of my function f of x. The other type of infinite limit is a vertical asymptote. And if you remember, a vertical asymptote is when the denominator equals 0, but not the numerator. Remember, if we have 0 over 0, that's an indeterminate form. But if we have a number over 0, then that's undefined. That is some sort of vertical line. It has an undefined slope. Let's take a look at some examples of this. So here we're looking at the limit as x goes to 1 from the right. Let's start by thinking through direct substitution. So if we directly substituted 1 into this limit, we'd get 4 over 0, which is undefined. So since we can't substitute 1 directly in, we sort of have to envision substituting in numbers that are really close to 1, but from the right-hand side. For example, let's think about substituting in 1.00001. Our numerator is a number really close to 4, and our denominator is practically 0. It's like 0.000001. If we take 4 divided by 0.00001, we get a really big number. And the closer we get to 1, the bigger that number becomes. That means that this limit is approaching positive infinity. As we get closer and closer to 1, our y values just get really, really big, and we're going to infinity. We can also look at the limit as x goes to 1 from the left. So this time we're plugging in numbers like 0.99999. Again, we have a positive number on top, and on the bottom, we're practically at 0, but 0.999 minus 1 is a negative number. So we have a number on top divided by practically 0, but negative on the bottom. Positive on top, negative on the bottom. We're going to negative infinity from this limit. And you can look at that over here on the graph again as well. As we approach 1 from the right, say this is x equals 1, our values are getting closer and closer to infinity, or approaching infinity. As we approach 1 from the left-hand side, our y values are shooting down to negative infinity. And that's what creates that vertical asymptote at x equals 1. Again, let's write down the formal definition of a vertical asymptote, which says that if the limit as x approaches some number from the right of your function, if that equals positive or negative infinity, or if the limit as x approaches some number from the left of your function equals positive or negative infinity, in the vertical line, x equals a is a vertical asymptote of your function. We can see here that as we approach, let's call this x equals a. As we approach a from the right, we go to infinity. As we approach a from the left, we go to negative infinity, and that creates that vertical asymptote.